Alright, so let's talk about parametric derivatives. So now we're getting into the serious differentiation. So let's say instead of having y is equal to something in terms of x, right? We're used to something like this. We're used to like y is equal to sine of x or y is equal to x squared. Instead of having that, let's say we had y is equal to t squared. And then we need something for x. So let's say we had x is equal to t to the power 4. Let's say we had that, right? Because we can't give y in terms of x. Let's say it was a more complicated function and it was difficult to give y in terms of x. So we can give y in terms of a parameter t, that's what a parameter is, t, and then x in terms of the same parameter t. So you can, if you try to sketch this, you could take different values for t. So you could take t is equal to 0 and then plot the point 0 and 0 on the curve. If you take t is equal to 2, then you would have x is equal to 2 to the power 4, which is 16, and y is equal to 2 squared, which is 4. So you would plot the point 16 and 4 on the curve, and then you can take all the points for t, and then you can have a curve for x and y. But we're not worried about plotting the curve, we're worried about getting the derivative. So how do you find dy by dx for that curve when you do plot it? Well, there are two ways to do it. One way is, you can see if you square this right here, you would get y squared is equal to t to the 4, right? Because if I square all of this, then I get y squared is equal to t to the power 4. And t to the power 4 is also equal to x, so you get y squared is equal to x. And then y is equal to x to the power half. And then you can take dy by dx from here, and you would end up getting a half times x to the power negative a half, which is equal to 1 over 2 square root x. So you can do it that way, but if the function is more complicated, then there is no way you're going to be able to arrange y in terms of x that easily. So let's see if we want to do it using t's. So remember, dy by dx, what was the chain rule? The chain rule was dy by dx is equal to dy by dt times dt by dx. Well, we can use this. So dy by dt, we can find that very easily from our original function was y is equal to t squared. Let me just write it again because I wrote on top of this. So y is equal to t squared and x is equal to t to the 4. So we can find dy by dt very easily. We can't find dt by dx, but what we can find is dx by dt, because you can just use the power rule on this right here. So let's do that first, and then we will see why that's useful. So dy by dt is equal to 2t. That's easy. And dx by dt is equal to 4t cubed. Right? Pretty simple. Now let's be smart about this chain rule. So we are multiplying two fractions, right? But isn't that the same as doing dy by dt divided by dx by dt? Because then if you divide two fractions, then you can multiply by the reciprocal. And the reciprocal of this is dt by dx, which is what we need to get dy by dx. So what if you did that? Is that equal to dy by dx? Yes, it is, because the dt's will cancel out. So let's do it. We have dy by dt and we have dx by dt as well. So we have 2t divided by dx by dt is 4t cubed. And that leaves us with, cancel the t, you're left with 1 over 2t squared, which is actually equal to, well, remember over here we go 1 over 2 square root x. What is the square root of x actually equal to? If you take the square root on both sides, then you end up getting x, or square root of x, is equal to t squared. And t squared is right here as well, so you actually end up getting 1 over 2, let's write that better, you end up getting 1 over 2 times square root of x. So you can see why this works. And it worked in our case over here. This was very easy to do using the normal method of just rearranging and then finding y in terms of x, because these are very simple. But what if you had a way more complicated function? Let's say you had something like y is equal to sine t plus 2t, and then x is equal to 1 over cos 2t. This will take you like so long just to get y in terms of x, and then to find the derivative of that would be so complicated. Instead, we can take the derivative of y with respect to t first, and the derivative of x with respect to t, and then just divide them by each other, and you will end up getting dy by dx. That's like an introduction to parametric differentiation. Let's do a question for parametric differentiation, so it makes more sense. It's question 4. The parametric equations of a curve are x is equal to cos theta over 2 minus sine theta, and y is equal to theta plus 2 cosine theta. Show that dy by dx is equal to 2 minus sine theta all squared. Okay, we know how to find dy by dx, so we need dy by dt divided by dx by dt. So we just have to take derivatives. Instead of t, we're doing theta, so it's the exact same thing. So let's do dy by d theta. Well, that's just 1 minus 2 sine theta. Right? That's just the derivative of theta plus 2 cos theta. The derivative of theta is 1. The derivative of 2 cosine theta is minus 2 times sine theta. So we have dy by d theta. That was simple. Let's find dx by dt. That's a bit more complicated. And here we'll have to use the quotient rule, if you remember from last time. So what do? So we take the derivative of this, which is negative sine theta, multiply it by 2 minus sine theta, and then from there we subtract the numerator, which is cosine theta, multiplied by the derivative of the denominator, which is negative cosine theta. And then of course all of this is divided by the denominator squared, which is 2 minus sine theta squared. 2 minus sine theta all squared. Okay, so we have a start. So what do? Let's simplify this first. So you can see you'll have negative 2 sine theta plus sine squared theta plus cos squared theta in the numerator. So that's actually equal to, well, sine squared plus cos squared is just 1, right? So you have 1 minus 2 sine theta in the numerator, and that's divided by 2 minus sine theta all squared. Okay, also this is, of course, all of this is also 2 minus sine theta all squared. So what can we do now? So we do dy by d theta divided by dx by d theta. dx by d theta. I wrote a t over here, but I meant theta. It's the exact same thing, just choosing what variable you want. There's no difference. So let's do it. So we have dy by d theta, which is 1 minus 2 sine theta. So we have 1 minus 2 sine theta. And you're dividing it by, this is dy by dx now. So you have dy by d theta divided by dx d theta. So if you're dividing by this right here, then you would do the reciprocal of this and multiply it. So you'd end up getting times 2 minus sine theta all squared divided by 1 minus 2 sine theta. We can see now you have 1 minus 2 sine theta in the denominator and the numerator. So you just cancel out. So you're left with dy by dx is equal to 2 minus sine theta all squared. So you can see you end up getting the correct answer. That's what you had to show. Now, arranging x in terms of theta and then putting that in for y, that's going to take very long because I don't even know if you can separate this that easily. So that's going to take so much longer, and to find the derivative will be even more complicated because you will have a very weird looking function over here. Instead, you can use parameters and just find dy by dx using the chain rule, and you end up getting a pretty simple answer. Oh yeah, that's it. There's no part B. So yeah, that's really all you need to know about parametric derivatives. So let's do one more example. Let's make our own example. Let's say we had y is equal to sine t and x is equal to cosine t. What's dy by dx? Well, we need to find dy by dx. Well, we have dy by dt, right? dy by dt is equal to the derivative of sine t, that's cosine t. And then dx by dt is equal to the derivative of cosine t, which is equal to negative sine of t. Right? So now we have to find dy by dx. So we do cosine t divided by negative sine t. So you're left with cosine t divided by negative sine t. This is dy by dx. Well, that's basically negative cotangent of t, right? Because cosine over sine is 1 over tangent, and then you have the negative, so it becomes negative cotangent of t. Or you can write that as negative 1 over tan t. We can do more examples if you want, but I don't think we should do any more because it's really very simple. You have it in terms of the parameters, you find the derivative of each of them, and then you just divide them by each other, and you should get the right answer. So yeah, that's parametric differentiation.